at most. Eventual consistency is perfectly acceptable here. If a seat shows as available for 1 extra second, that's fine. For booking, we need strong consistency. We absolutely cannot double book a seat. 2 users selecting the same seat simultaneously must have exactly 1 succeed. We also need to handle sudden traffic spikes. A popular artist going on sale can bring millions of users simultaneously, which is 10,000 times our normal booking throughput. These 2 requirements, high availability for reads and strong consistency for writes, will drive most of our design decisions. Let's think about scale. Ticketmaster has around 100 million registered users, with roughly 5 million active on any given day. We expect around 50 million event page views per day. That's about 580 reads per second on average. Ticket sales run about 500,000 per day, which is only about 6 bookings per second normally. But normal is not our design point for booking. The real challenge is the spike scenario. When a major artist puts tickets on sale, 2 million or more users hit buy simultaneously. Peak booking demand can hit 50,000 requests per second in the first 60 seconds, a 10,000 times multiplier over our average load. For storage, the numbers are actually manageable. Events data runs about 10 gigabytes per year. Tickets and bookings are under 100 gigabytes per year. A search index would be around 50 gigabytes. Storage is not our bottleneck. Traffic is. This tells us we need aggressive caching for reads and a fundamentally different strategy for surge traffic on bookings. Let's define our core entities, the data model. We have 6 entities: user, standard, ID, email, name, created timestamp, event, ID, venue ID as a foreign key, title, start time, total seats, and an on sale at timestamp, which we'll need for surge handling. Venue, ID, name, city, capacity, address. Performer, ID, name, genre. Events and performers have a many-to-many relationship through an event performers join table. Ticket, this is the critical entity. ID, event ID, seat row, seat number, price, and status. The status field is an enum, available, reserved, or sold. This drives our booking logic. Booking links a user to a ticket. ID, user ID, ticket ID, booking status, reserved until timestamp, and confirmed at timestamp. The reserved until field is how we implement our reservation timeout pattern. One note on schema. Tickets and bookings live in a separate Postgres database from events and venues. This keeps our write-heavy booking path isolated from read-heavy event data. Now the API design. We have 4 core endpoints. Get/events/event ID returns full event details, the event record, venue, performers, and available ticket tiers. This will be heavily cached. Get/events/search takes query parameters, queue for a keyword, location, date range, page, and limit for pagination. This hits Elasticsearch under the hood for fast full-text search. Post/bookings/reserve takes a ticket ID and user ID. This is step 1 of our 2-phase booking. It atomically marks the ticket as reserved and returns a booking ID along with a reserved until timestamp. 10 minutes from now. The client shows the user a countdown timer. Post/bookings/confirm. Takes the booking ID and a payment token from Stripe. It charges the card and, on success, marks the ticket as sold and the booking as confirmed. The 2-phase design is key. Reserve locks the seat without touching payment. Confirm handles the slow, failure-prone payment step. If anything goes wrong, the reservation expires automatically. Now, the high-level architecture. Clients, web and mobile, hit our API gateway and load balancer. The gateway handles auth, rate limiting, and routing. Behind the gateway, we have 3 microservices. The event service handles all read traffic for events, browsing event pages. It sits in front of a Postgres database for events, venues, and performers. We add a Redis cache in front of it with a 5-minute TTL. Popular event pages never touch the database. The search service handles event search queries. It queries an Elasticsearch cluster, which holds a full-text index of all events. Elasticsearch is synced from Postgres via change data capture. When an event is created or updated in Postgres, the change propagates to Elasticsearch within about 1 second. The booking service handles reservations and confirmations. It writes to a separate Postgres database for tickets and bookings. It uses Redis to manage reservation locks with TTL. For payment, it calls out to Stripe. We also add a CDN for static assets, event images, venue maps, to reduce load on origin servers. This architecture cleanly separates the read path from the write path, letting us scale each independently. Let's deep dive into the reservation and booking flow, the hardest part of this design. The core problem: 2 users select the same seat at exactly the same moment. Payment takes 10 to 30 seconds. How do we prevent both from succeeding? The naive approach is to hold a database transaction open for the entire payment duration. Select the ticket for update, call Stripe, then commit. This is a disaster at scale. The database row is locked for 30 seconds. All other buyers for that seat are blocked. Under load, you get timeout cascades and your booking service falls over. Instead, we use the reservation pattern. When a user hits reserve, the booking service does 2 things atomically. First, it sets a key in Redis, ticket:ID, to reserved with a TTL of 600 seconds, 10 minutes. Second, it does a conditional update in Postgres. Update ticket set status equals reserved where status equals available. This Postgres update is fast, milliseconds. If it succeeds, we own the seat. The client gets back a booking ID and a countdown timer. They have 10 minutes to pay. Meanwhile, if another user tries to reserve the same seat, the Postgres update fails because the status is no longer available. They get a conflict error immediately. When the user confirms, the booking service calls Stripe, and on success, updates the ticket to sold and deletes the Redis key. If the user abandons, the Redis TTL expires. A cleanup job resets the ticket to available. The seat goes back on sale automatically. No manual intervention, fully idempotent. For edge cases, payment failure leaves the reservation intact until TTL. Network timeouts are handled by retrying confirm with the same booking ID. Race conditions are resolved by the Postgres conditional update. Exactly 1 writer wins. Let's talk about scaling reads and search. For event page reads, we add Redis cache in front of the event service using cache aside. On a request, check Redis first. Cache hit, return immediately, sub-millisecond. Cache miss, query, Postgres, populate the cache, return. With a 5-minute TTL, popular events are almost always cache hits. Postgres read traffic drops by over 90% under load. For search, Elasticsearch gives us full-text search across event titles, venue names, and performer names. It also handles geo-queries for location-based filtering and date range filters. Elasticsearch scales horizontally, add nodes, rebalance automatically. We sync the index from Postgres via change data capture. A 1-second lag in search results is completely acceptable. For the Postgres database itself, we add read replicas. All writes go to the primary, only the booking service writes, and only for bookings. All reads are distributed across replicas. The primary is protected. Stateless services, event service, search service, scale out horizontally behind the load balancer with no coordination needed. The booking service needs more care since it coordinates Redis locks, but it too can scale out as long as Redis is the shared lock store. Let's talk about the surge problem, the hardest operational challenge for Ticketmaster. A major concert goes on sale at 10 a.m. 2 million users have been waiting on the page. They all click buy simultaneously. The system receives 50,000 booking requests per second for the first 60 seconds. Our normal capacity is 50 per second. Without mitigation, the booking service is immediately overwhelmed. The whole system falls over. The solution is a virtual waiting room. When a high-demand event enters on sale, incoming users are routed to the waiting room service instead of directly to booking. The waiting room assigns each user a queue position, stored in a Redis sorted set, sorted by arrival timestamp for fairness. The system drains the queue at a controlled rate, say 100 users per second. When it is their turn, users get a time-limited checkout window and can proceed to reserve a ticket. Users who are waiting see their real-time queue position through server-sent events, a single long-lived HTTP connection that the server pushes updates to every few seconds. The user sees, "You are number 8,000 in queue, approximately 4 minutes." For fairness and anti-abuse, per-user rate limiting at the API gateway, CAPTCHA at queue entry for high-demand events, purchase limits per account of typically 4 tickets maximum, and authentication required before joining the queue. The key insight is that the waiting room absorbs the spike externally. The booking service sees steady, controlled throughput regardless of how many people are trying. The user experience degrades gracefully. Instead of errors, users wait in a fair queue. Let's bring it all together. Our key architectural decisions: the two-phase reservation pattern, reserve with Redis TTL and confirm after payment, eliminates long database locks and gives us automatic timeout recovery. We separate read and write paths completely. The event service serves reads from Redis cache and Postgres replicas. The booking service is the only writer, isolated to its own database. Elasticsearch handles search, including full text, geo, and date range, synced from Postgres with acceptable lag. Redis is doing double duty, read cache for event pages and reservation lock store for bookings. These are separate Redis clusters to prevent interference. The virtual waiting room turns catastrophic failure modes, 10,000 times traffic spikes, into a fair queuing problem that the system handles gracefully. On the trade-offs, booking is strongly consistent, using a conditional Postgres update as our arbiter. Read traffic is eventually consistent, as cache TTL means a few seconds of staleness, which is fine. The reservation TTL of 10 minutes is a product decision. Shorter hurts user experience, longer keeps seats off the market too long. In an interview, lead with the booking flow. Mention the two-phase pattern early. Proactively bring up Elasticsearch. Be ready to discuss idempotency, edge cases, and the surge problem. Thank you for watching.